In the quiet reaches of the cosmos, we experience time as a constant and invisible, relentless river, carrying us from a known past toward an uncertain future. It is the fundamental heartbeat of human existence, the one metric we cannot negotiate or escape. Yet our perception of this flow is entirely tethered to the environment in which we evolved. A world of gentle gravity and predictable motion. When we turn our gaze toward the great gravitational wells of the deep universe, we find places where this primary rule of reality begins to fray. The event horizon of a black hole represents more than just a physical boundary of light and shadow. It is the ultimate limit of our understanding of now. We often speak of these celestial giants as consumers of matter, but their most profound influence is their mastery over the clock itself. To understand why time appears to stand still at the edge of the abyss, we must first confront the fragility of our own temporal intuition. We must strip away the layers of how we believe the universe functions and look closely at the relationship between mass and the very fabric of the void. In the following journey, we will trace the path of a single moment as it approaches the point of no return, uncovering a reality where the sequence of events is no longer a shared experience, but a fractured, beautiful distortion of the laws of nature. The universe does not tick. Somewhere in the architecture of human thought lies a quiet conviction that time is universal, that there exists, woven into the fabric of reality itself, a singular rhythm and invisible clock against which all events are measured. We imagine that when something happens here on this pale blue dot, it happens now, and that this same now extends outward, past the moon, past Mars, past the silent drift of distant galaxies, uniting all of existence in a shared present moment. It is a comforting geometry, a stage upon which the cosmos performs, with every actor moving in lockstep to the same hidden metronome. But the universe does not work this way. This assumption that time flows uniformly, that the present moment is a universal plane slicing through reality, is so deeply embedded in human perception that it feels less like a belief and more like a fact. We experience time as a river, carrying us forward at a steady pace, and we assume that everyone else, everywhere else, floats in the same current. When we schedule a meeting, board a flight, or watch a star explode in a telescope, we speak of these events as though they occupy points on a universal timeline, as though the word now has the same meaning whether spoken on Earth, whispered in the rings of Saturn, or broadcast from the edge of the observable universe. Physics, however, tells a different story. The present moment is not cosmic. It is local. It is yours and mine and the planets. But it is not the galaxies. It is not the universes. The idea that time progresses at the same rate for everyone, everywhere, regardless of circumstance, is an illusion born from the narrowness of human experience. We live our lives in a gravitational field so gentle, at speeds so modest, that the malleability of time remains hidden. The differences are real, but imperceptibly small. So we built our intuitions in a universe that seemed absolute, never suspecting that we were living in a special casa, slow, flat, forgiving pocket of spacetime where the deeper rules were veiled. It was not always obvious that this assumption was wrong. For millennia, thinkers imagined time as an immutable constant, a dimension wholly separate from space. Isaac Newton described it as flowing equably without relation to anything external. Time, in this view, was a river that carried all things equally, indifferent to the boats it bore. It did not bend, it did not slow, it simply was. And for the physics of Newton's era, this was sufficient. The motions of planets, the arc of cannonballs, the swing of pendulums, all of these could be predicted with exquisite precision under the assumption that time was absolute. But the universe is not Newtonian. The first crack in this edifice appeared not from philosophy, but from light. In the late 19th century, physicists discovered something strange. Light always travels at the same speed, no matter how fast you are moving when you measure it. This was deeply troubling. If you run toward a beam of light, Newtonian intuition says you should measure it moving faster. If you run away, it should seem slower. But light refuses to obey. It moves at the same speed whether you are standing still, hurtling forward, or spinning in circles. The speed of light is a constant, unbending, and absolute, even as everything else shifts around it. This simple fact, this stubborn constancy, shattered the old order. If the speed of light is always the same, then something else must give. And what gives is time itself. Albert Einstein formalized this revelation in 1905 with his theory of special relativity. The mathematics were elegant, but the implications were startling. Time, Einstein showed, is not a fixed backdrop. It is a dimension intertwined with space, and it flexes depending on motion. Two observers moving relative to one another will measure time differently. Not because their clocks are broken, but because time itself runs at different rates depending on how fast you are traveling. A person on a speeding spacecraft will age more slowly than someone standing still. Their heartbeat, their thoughts, the decay of particles in their body, all of it proceeds at a different tempo. Not subjectively, not metaphorically, but actually. There is no universal now. There is only your now, and mine, and theirs. This realization dissolves the intuitive picture of a synchronized cosmos. Imagine two events occurring in distant parts of the universe, one star exploding in a galaxy far to the north, another collapsing into darkness in the south. We might ask, which happened first? The answer, it turns out, depends on who is asking. One observer, moving in a particular direction, might see the northern star explode before the southern one collapses. Another observer, moving differently, might see the reverse. And a third, moving yet another way, might conclude that the two events occurred simultaneously. All three are correct. There is no cosmic referee to declare which event truly happened first, because the sequence of distant events is not absolute, it is relative. It's not a trick of perception. 'Tis the structure of reality. The implications ripple outward. If time is relative, then the present moment cannot extend uniformly across space. There is no cosmic now that synchronizes the universe. The past, present, and future are not universal categories, but local experiences shaped by motion and gravity. What you call now is a personal horizon, a slice through spacetime that belongs to you alone. An astronaut hurtling past Earth at nearly the speed of light would not share your present. Their now would tilt away from yours, encompassing events you consider future and excluding moments you believe are simultaneous. The faster they move, the more their present diverges from yours, until the very notion of a shared timeline becomes meaningless. And motion is only part of the story. Einstein's next insight, published a decade later in his general theory of relativity, revealed that gravity mass itself also warps time. Not metaphorically, but literally. A clock placed on the surface of the Earth runs slower than a clock floating in the emptiness of space. The difference is minuscule, mere billionths of a second per day, but it is real. Satellites orbiting overhead must account for this discrepancy, adjusting their timekeeping to compensate for the fact that time moves faster up there than it does down here. Without these corrections, GPS systems would drift out of alignment within minutes. The coordinates they provide would blur, streets would shift, navigation would collapse. The technology we rely on daily exists only because we have learned to accommodate the flexibility of time. The stronger the gravitational field, the more pronounced the effect. On the surface of a neutron star, where gravity is so intense that a teaspoon of matter weighs as much as a mountain, time slows dramatically. A clock placed there would tick noticeably slower than one held in your hand. An hour on the neutron star might correspond to several hours far away. This is not a malfunction. This is time itself, shaped by the curvature of spacetime, bending under the weight of mass. The universe, then, is not a stage with a single timeline. It is a landscape of countless timelines, each flowing at its own rate, influenced by motion and gravity. Every object, Every particle, every observer carries their own clock, their own present moment. These clocks do not synchronize. They cannot. The geometry of space-time forbids it. Time is not a universal dimension stretching uniformly across the cosmos. It is a local phenomenon, a personal experience, woven into the fabric of space itself. This realization dismantles the notion of a master clock. There is no central timekeeper, no cosmic metronome against which all events are measured. The ticking you experience here, now, on this planet, is not the ticking of the universe. It is the ticking of this place, this gravitational well, this particular path through space-time. Move to a different location, accelerate to a different speed, and time will flow differently. Not in appearance, but in substance. And if time is not universal, then neither is simultaneity. The idea that two events can occur at the same time loses its absolute meaning. Simultaneity becomes a matter of perspective, dependent on the observer's motion and position in a gravitational field. What one observer measures as simultaneous, another measures as sequential. The present moment does not extend across the universe like a plane slicing through reality. It bends, twists, fragments into a mosaic of overlapping nows, none of them privileged, none of them absolute. This is the nature of space-time. The consequences become extreme near-massive objects. A planet bends space-time gently, creating the subtle warping that keeps our satellites synchronized. A star bends it more. But a black hole, a concentration of mass so dense that it collapses into a singularity, bends space-time to the breaking point. Near a black hole, the distortion becomes so severe that time itself begins to behave in ways that defy intuition. Clocks slow to a crawl. Seconds stretch into hours. The present moment, already fragile and relative, fractures entirely. Consider an observer falling toward a black hole. From their perspective, nothing feels unusual. They do not sense time slowing. Their heartbeat remains steady. Their thoughts proceed normally. They experience their own present moment as they always have. But to someone watching from a safe distance, far from the black hole's influence, the falling observer appears to slow down. Their descent becomes sluggish. Their movements stretch out, frame by frame, as though reality itself is stuttering. The light from the falling observer reddens, its wavelength stretched by the extreme curvature of space-time. Eventually, the observer appears to freeze entirely, suspended just above the black hole's event horizon, locked in a moment that never quite ends. This is not an optical illusion. It is the natural consequence of time's relativity. The distant observer and the falling observer no longer share a timeline. Their presents have diverged so completely that they occupy different realities. For the distant observer, the falling observer never crosses the horizon. They remain there, frozen, fading into dimness as time stretches toward infinity. For the falling observer, nothing prevents their crossing. They pass through the horizon and continue inward, encountering whatever lies beyond, experiencing a future the distant observer will never witness. The two timelines have decoupled. This decoupling is permanent. There is no reconciliation, no moment when the two observers' clocks realign. The present moment, once shared or at least overlapping, has split. The falling observer S now extends into a region of spacetime that the distant observer S now can never reach. The black hole has severed their connection, not through distance alone, but through the fundamental geometry of time itself. And this is where the illusion of simultaneity fully collapses. If time is not universal, if the present moment is not a cosmic truth, then the boundary between past, present, and future becomes negotiable. What has already happened for one observer may still lie in the future for another. What is simultaneous for one is sequential for the next. The architecture of reality is not a single timeline progressing uniformly from past to future, but a web of intertwined timelines, each flowing at its own rate, shaped by the curvature of spacetime. Near a black hole, this web unravels. The extreme gravitational field does not merely slow time, it reshapes the very structure of causality. Events that seem simultaneous to a distant observer are spread across an eternity for someone closer. The present moment becomes a gradient, a spectrum, a dissolving boundary between what is and what was. And at the event horizon, that boundary disappears entirely. Time, as we understand it, ceases to function in the familiar way. The future becomes unreachable from the outside. The past becomes inescapable from within. This is not science fiction. This is the mathematical consequence of general relativity. Confirmed by observation, encoded in the behavior of light and matter near massive objects. The universe does not have a universal clock. It never did. And in the presence of a black hole, the absence of that clock becomes undeniable. Time fractures, the present moment shatters, and the illusion of simultaneity, the comfortable belief that we all share the same, now fades into the horizon, leaving only the cold truth of relativity in its wake. The mind is a product of its environment. Every thought you form, every image you conjure, every intuition about how the world works, all of it has been shaped by the conditions under which your brain evolved. For millions of years, human ancestors navigated a world of predictable rhythms. The sun rose and set, seasons cycled, hearts beat at steady intervals, cause preceded effect. Time flowed forward, never backward, never sideways, always at the same perceptible rate. In this environment, the brain developed shortcuts, heuristics that allowed survival without requiring a deep understanding of underlying physical laws. You do not need to comprehend the curvature of spacetime to catch a falling object or estimate when a predator will reach you. You only need a functional model, a simplified map of reality that works well enough to keep you alive. And so the brain built one. This model is remarkably effective within its domain. It allows you to navigate three-dimensional space with ease, to predict trajectories, to coordinate movement, to organize memory along a linear timeline. But it is not the territory. It is a map drawn for a specific terrain, Earth's surface, under Earth's gravity, at Earth's speeds. Venture beyond these conditions, and the map begins to fail. Not because reality changes, but because the map was never complete to begin with. Time, in the brain's model, is a river. It flows in one direction, carrying moments from past to future at a constant rate. Events are strung along this river like beads on a thread, each occupying a distinct position. You remember what came before. You anticipate what comes next. The present moment feels like a moving boundary, a knife edge separating the known from the unknown. This mental architecture works seamlessly in everyday life. It allows you to plan, to regret, to hope. But it is an approximation, a cognitive tool optimized for survival in a narrow band of physical conditions. The problem arises when this approximation is mistaken for truth. Human perception operates within profound constraints. Vision captures only a thin slice of the electromagnetic spectrum. Hearing registers vibrations within a limited range of frequencies. The sense of time is no different. You perceive time as linear because your brain evolved in an environment where deviations from linearity were too small to matter. The gravitational field at Earth's surface is weak. The speeds at which humans move are glacial compared to the speed of light. Under these conditions, the warping of space-time is imperceptible. Time appears absolute because the distortions are hidden beneath the threshold of human awareness. But the universe is not obligated to conform to this perception. Consider the way the brain processes spatial dimensions. You navigate three dimensions with ease, left and right, forward and back, up and down. You can visualize a cube, rotate it mentally, understand its geometry. But ask the brain to visualize four-dimensional space, and it stumbles. Not because four-dimensional space is illogical or non-existent, but because evolution provided no survival advantage in perceiving it. There were no predators lurking in the fourth dimension, no food sources accessible only through hypergeometric thinking. And so the brain never developed the wiring to intuitively grasp higher dimensional structures. Time, in the framework of general relativity, is not separate from space. It is the fourth dimension of a unified space-time manifold. Objects do not move through space and time. They move through space-time, tracing paths called world lines. Your entire existence, from birth to death, is a single curve in this four-dimensional structure. What you perceive as the present moment is simply the particular cross-section of your world line that your consciousness happens to occupy at this instant. But the brain cannot visualize this. It cannot see the world line as a whole, cannot perceive the geometry of spacetime as it truly is. It can only experience one slice at a time, stitching these slices together into the illusion of a flowing present. This limitation becomes severe when confronting the extreme curvature near a black hole. The mathematics of general relativity describes spacetime as a flexible fabric, bent and stretched by the presence of mass. Near a black hole, this curvature becomes so extreme that the familiar rules of geometry break down. Straight lines become circles. Light bends back on itself. The dimension we call time mixes with the dimensions we call space in ways that defy visualization. The brain, accustomed to flat spacetime and gentle curvatures, finds no foothold here. It cannot picture what it means for time to slow asymptotically, for the future to become unreachable, for simultaneity to collapse into paradox. And yet, the mathematics remains consistent. The equations describe a coherent structure, one that can be analyzed, predicted, tested, but the human mind, unaided, cannot see it. We are left trying to comprehend a geometry for which we have no intuitive sense, using cognitive tools built for a world that no longer applies. Language itself becomes an obstacle. Words like later, soon, eventually, all of these carry implicit assumptions about the flow of time. They presume a shared timeline, a universal ordering of events. But near a black hole, these words lose their meaning. What does later mean when your clock and mine no longer agree? What does eventually mean when an event recedes infinitely into the future for one observer while occurring immediately for another? The vocabulary we use to describe temporal relationships is calibrated for the narrow regime in which humans evolved. It is insufficient for the broader reality. Even the word now becomes ambiguous. We use it to denote the present moment, but the present moment is not a universal fact. It is a local experience, a cross-section through your particular world line. When you say now, you are referring to a hypersurface in spacetime that depends on your velocity, your gravitational environment, your path through the cosmos. Someone else's now may not overlap with yours. Near a black hole, the divergence becomes so extreme that the concept ceases to function. There is no shared now between the observer falling inward and the observer watching from afar. Their presents have separated, each following its own trajectory through spacetime, never to realign. The brain struggles with this because it was not designed to handle it. Evolution did not prepare us for a universe where time is negotiable, where the future can be unreachable, where cause and effect become entangled in gravitational fields. These are not intuitive concepts. They are mathematical truths, revealed through equations and confirmed by observation, but they remain alien to direct experience. You cannot feel space-time curvature the way you feel the pull of gravity. You cannot see time dilation the way you see a sunset. These phenomena exist beyond the range of human perception, accessible only through instruments and abstractions. And this reveals something profound about the nature of understanding itself. Knowledge and intuition are not the same thing. You can learn the mathematics of general relativity, work through the equations, derive the predictions, confirm them against observation. You can understand, intellectually, that time dilates near massive objects, that simultaneity is relative, that the event horizon represents a boundary beyond which information cannot escape. But understanding intellectually is not the same as grasping intuitively. The brain can process the logic without ever truly visualizing the phenomenon. It can accept the conclusion without being able to picture the mechanism. This gap between knowledge and intuition is not a failure of intelligence. It is a limitation of biological architecture. The human brain is a pattern recognition engine, optimized for detecting regularities in sensory data and extrapolating from past experience. It excels at tasks where the patterns are within the range of evolutionary relevance, predicting the arc of a thrown stone, recognizing a face in a crowd, estimating the ripeness of fruit. But when confronted with patterns that lie outside this range, the brain has no template to apply. It can manipulate symbols, follow logical chains, perform calculations, but it cannot generate the visceral sense of comprehension that comes from direct perception. Near a black hole, this disconnect becomes unavoidable. The environment is so far removed from the conditions under which human cognition evolved that intuition simply fails. You cannot trust your gut. Your instincts, honed over millennia of life on a stable planet under gentle gravity, offer no guidance. They tell you that time flows uniformly, that events have a definite order, that the future is always accessible if you wait long enough. All of these intuitions are wrong in the vicinity of an event horizon. They are relics of a simpler regime, useful approximations that break down under extreme conditions. Recognizing this limitation is the first step toward intellectual humility. The event horizon is not just a physical boundary, it's a cognitive one. It marks the edge of what the human mind can comfortably envision. Beyond it lies a regime where the familiar rules no longer apply, where time and space intertwine in ways that defy visualization, where the narrative structure of past presents future dissolves into something more complex and strange. This is not a defect of the universe. It is a defect of our perceptual apparatus. Consider how the brain represents time internally. Neurological studies suggest that the perception of duration is constructed, not measured. The brain does not contain a single master clock ticking away in perfect synchrony with external reality. Instead, it integrates signals from various neural processes' heartbeat. Circadian rhythms, sensory input, synthesizes these into a subjective experience of time passing. This experience is malleable. Moments of intense focus seem to contract. Periods of boredom stretch out. The brain's sense of time is not an objective readout, but a constructed narrative, assembled after the fact to create a coherent story of events. This constructed nature of temporal perception makes it even less suited to comprehending relativistic effects. When a clock slows near a black hole, it is not the subjective experience of time that changes for the observer, it is the objective flow of time itself, as measured against distant reference frames. But the brain has no mechanism to perceive this distinction. It cannot feel the difference between subjective and objective time because its entire model of time is inherently subjective. It knows only what it experiences, and what it experiences is always local, always tied to its own frame of reference. Philosophy has long grappled with this tension. Immanuel Kant argued that space and time are not features of the external world, but forms of human intuition structures imposed by the mind to organize sensory experience. Modern physics suggests he was partially correct. The way we perceive time is indeed shaped by the architecture of our cognition. But the relativistic nature of time is not merely a perceptual phenomenon. It is woven into the fabric of reality itself, independent of whether anyone is present to observe it. Clocks near a black hole slow down whether or not a conscious mind is watching. The event horizon exists whether or not anyone crosses it. The universe does not require human perception to function. And yet, human perception is the only tool we have for engaging with the universe directly. We can extend that perception with instruments, clocks, telescopes, particle detectors, but even these extensions must ultimately be translated back into terms the brain can process. The readings on a clock, the images from a telescope, the data from a detector, all of these must be interpreted, and the interpretation is constrained by the same cognitive limitations that shape raw perception. We see the numbers, read the graphs, analyze the patterns, but we do not experience the four-dimensional geometry they describe. We remain, always, creatures of three spatial dimensions and one temporal dimension, peering into a reality that extends beyond our native perceptual range. This creates a paradox. The deeper we probe into the nature of time, the more we rely on abstractions that our brains cannot fully internalize. We can derive the Schwarzschild metric, calculate the time dilation factor at a given distance from a black hole, predict the behavior of light and matter near the event horizon. But we cannot visualize what it would feel like to exist in such a regime because the feeling would be nothing. To the observer falling inward, time flows normally. It is only from the outside, from the perspective of a distant observer, that the distortion becomes apparent. And even then, it is not perceived directly. It is inferred from the behavior of light, the ticking of clocks, the redshift of photons. The event horizon, then, is a threshold where human intuition meets its limit. It is the point beyond which the brain's evolved model of reality can no longer function as a guide. The mathematics continues, unperturbed. The equations describe what happens past the horizon with the same precision they describe what happens far away, but the mental image fails. The brain cannot follow the trajectory. It cannot reconcile the idea that an observer can cross the horizon from their own perspective while appearing to freeze from the perspective of someone else. The two narratives seem incompatible, contradictory, paradoxical. And in a sense, they are if you insist on forcing them into the framework of absolute time and universal simultaneity. But that framework is the problem. It is a relic of terrestrial logic, a cognitive artifact that evolution etched into the structure of human thought. It served us well on the savannah, allowed us to build civilizations, construct technologies, explore the cosmos. But it was never the whole truth. It was always an approximation, valid only within a narrow range of conditions. Step outside that range, approach a black hole, accelerate to relativistic speeds, and the approximation breaks down. The map no longer matches the territory. The brain's model of time diverges from time itself. Accepting this divergence requires a kind of cognitive surrender. You must acknowledge that your intuitions, however compelling, are not reliable guides to the fundamental structure of reality. You must set aside the visceral sense of how things should work and trust instead the abstract, mathematical description of how things do work. This is not easy. The brain resists, clings to its models, tries to force the universe into familiar patterns. But the universe does not care. It operates according to principles that predate human cognition, principles that remain true whether or not any mind exists to comprehend them. And so we are left with a choice. We can retreat into the comfort of everyday experience, where time feels absolute and the present moment seems universal. Or we can venture into the uncomfortable territory beyond, where the clock begins to fail, where simultaneity fractures, where the future becomes unreachable and the past inescapable. This territory is not hospitable to human intuition. It offers no familiar landmarks, no reassuring patterns. But it is the territory where black holes reside. And if we wish to understand what it means to approach the event horizon, we must leave the safety of our evolved perceptions behind and follow the mathematics into the dark. Mass is not a thing resting on spacetime. Mass is spacetime bent into a particular shape. This is the central insight of general relativity, and it remains one of the most profound reversals in the history of physics. For centuries, gravity was understood as a force and invisible tether pulling objects toward one another across empty space. Newton's law of universal gravitation described this force with mathematical precision, allowing astronomers to predict the motion of planets, the trajectory of comets, the rhythm of tides. But Newton himself acknowledged that his equations described what gravity did, not why it existed. He could quantify the attraction between masses, but could not explain the mechanism by which that attraction operated. The force simply was, acting instantaneously across any distance, without apparent medium or delay. Einstein proposed something different. Gravity, he suggested, is not a force at all. It is geometry. The universe is not a static stage upon which matter performs. It is a dynamic fabric spacetime that bends and flexes in response to the presence of mass and energy. When you place an object in space, you are not simply occupying a location. You are distorting the structure of spacetime itself, creating a curvature that extends outward, influencing everything nearby. Other objects do not fall toward you because of some mysterious pulling force. They fall because the geometry of spacetime has changed. And the straightest possible path through that curved geometry leads them in your direction. This is not metaphor, it is description. Imagine spacetime as a taut rubber sheet. In the absence of mass, the sheet is flat. A marble rolled across it would travel in a straight line, undisturbed. But place a heavy sphere on the sheet, and it sinks, creating a depression. The sheet is no longer flat. It has curvature. Now, if you roll the marble across the sheet, its path bends. Not because the sphere is pulling on the marble, but because the marble is simply following the straightest available path through the curved surface. From the marble's perspective, it is moving in a straight line. But from an outside perspective, observing the sheet as a whole, the path appears curved. The marble circles the depression, tracing an orbit, not because of a force, but because of geometry. This analogy captures the essence of general relativity, though it simplifies profoundly. Spacetime is not a two-dimensional sheet, but a four-dimensional manifold. The curvature is not simply a dip in a surface, but a warping of the entire structure space and time together. And crucially, the curvature does not only affect spatial paths, it affects the flow of time itself. This is where the analogy fails, and where the true strangeness of general relativity emerges. When mass curves spacetime, it does not curve space and time equally. The temporal dimension bends differently than the spatial ones. Near a massive object, time slows. Not because clocks malfunction, but because the rate at which time progresses, the fundamental tempo of cause and effect, changes with the curvature of spacetime. The closer you are to a mass, the more pronounced the curvature, and the slower time flows relative to regions farther away. This temporal distortion is gravity. It is tempting to think of gravity as a downward pull, a force dragging objects toward the ground. But from the perspective of general relativity, what we call gravity is simply the consequence of moving through curved spacetime. You are not being pulled toward the Earth. You are following a geodesica, path of least resistance through the curved geometry. The Earth has distorted spacetime in such a way that the straightest path forward in time leads you downward in space. You fall not because a force acts upon you, but because the structure of reality itself is tilted. The mathematics formalize this relationship in Einstein's field equations, a set of 10 interrelated differential equations describing how the distribution of mass and energy determines the curvature of spacetime. The equations are complex, but their essence can be summarized. Matter tells spacetime how to curve, and curved spacetime tells matter how to move. This feedback loop is the entirety of gravity. There is no additional mechanism, no hidden force. The geometry is the explanation. And within this geometry, time is not merely a passive coordinate. It is an active participant, curving in response to mass, just as space does. In regions of weak curvature, far from massive objects, time flows at what we might call its baseline rate. But approach a massive object, and the curvature increases. Spacetime bends more sharply. The temporal dimension warps. Time slows down. This is measurable. Atomic clocks placed at different altitudes on Earth tick at different rates. A clock at sea level runs slower than a clock on a mountaintop. The difference is minuscule, mere nanoseconds per day, but it is real and consistent. The clock at sea level is deeper in Earth's gravitational well, experiencing stronger curvature and thus progressing through time more slowly. Satellites in orbit, farther from Earth's mass, experience weaker curvature and faster time. Engineers must account for this discrepancy when designing GPS systems, adjusting the satellite clocks to compensate for the relativistic time dilation. Without these corrections, the system would fail. The same principle applies universally. On the surface of a more massive planet, time would flow more slowly than on Earth. On a neutron star, where gravity is millions of times stronger, the slowdown would be dramatic. A clock placed there would tick noticeably slower than one held in your hand far from any mass. This is not a trick of perception or a limitation of the clock. This is time itself, flowing at a different rate, shaped by the curvature of spacetime. And the curvature can become extreme. Near a black hole, the distortion of spacetime is so severe that the geometry itself begins to exhibit properties that seem paradoxical from the perspective of flat spacetime intuition. The depression in the fabric, if we return to the analogy of the rubber sheet, becomes infinitely steep. The curvature does not merely slow time. It bends the temporal dimension so radically that the distinction between space and time begins to blur. Directions that were purely spatial and flat spacetime acquired temporal components near the black hole. The closer you get, the more the geometry insists that your future trajectory leads in one specific direction, inward. This inward direction is not a choice. It is written into the structure of spacetime itself. Far from a black hole, you can move freely in any spatial direction. Forward, backward, left, right, up, down, all of these are available to you. Time, meanwhile, flows in only one direction. You move inexorably from past to future, unable to reverse course. This asymmetry is fundamental. Space offers freedom. Time offers none. But near a black hole, this distinction erodes. The spatial dimension pointing toward the singularity begins to acquire the character of time. It becomes less like a direction you can choose and more like a direction you must follow. At the event horizon, the transition is complete. The inward direction is no longer spatial in the conventional sense. It has become temporal. Crossing the horizon does not merely place you in a new location. It places you on a trajectory through time that leads inevitably toward the singularity. Just as you cannot avoid moving from this moment to the next, you cannot avoid moving from the horizon to the center. The singularity is not in front of you in space. It is ahead of you in time. 'Tis your future, unavoidable and absolute. This is the geometric reality of the event horizon. It is not a barrier in the sense of a wall or a surface. It is a threshold in the curvature of spacetime, a boundary beyond which the temporal dimension has been so profoundly warped that escape becomes impossible. Not because something pulls you inward, but because every path forward in time leads deeper into the black hole. There is no outward direction anymore. Outward has ceased to be a temporal option. To understand this, consider the nature of a geodesic. In flat spacetime, a geodesic is simply a straight line, the shortest path between 2 points. In curved spacetime, a geodesic is still the straightest possible path, but what counts as straight depends on the geometry. Near a massive object, geodesics curve. A planet orbits a star not because a force deflects it, but because the geodesic path through curved spacetime happens to be an ellipse. The planet is moving straight through spacetime. It is spacetime itself that is curved. Inside the event horizon, all future-directed geodesics point inward. There are no paths through time that lead outward. You can fire your engines, accelerate in any direction you choose, but you cannot alter the fundamental geometry. You cannot create a geodesic that escapes, because spacetime itself forbids it. The curvature is too extreme. The temporal dimension has been bent so sharply that the future exists only in one direction, toward the singularity. This is not a failure of propulsion. It is a consequence of geometry. Even light, which always travels along geodesics at the maximum possible speed, cannot escape. Photons emitted inside the event horizon follow the curvature of spacetime, and every future-directed path leads inward. They do not slow down. They do not lose energy in the conventional sense. they simply move through a geometry in which outward is no longer a direction that exists in the future. The implications are profound. The event horizon is not merely a point of no return. It is a region where the structure of causality itself has been fundamentally altered. Cause and effect still operate, but they operate within a geometry so warped that outcomes we would consider inevitable in flat spacetime are no longer possible. The horizon represents a boundary in the causal structure of the universal line beyond which certain events cannot influence certain other events, not because of distance or barriers, but because the geometry does not permit the necessary connections. From the outside, this manifests as an asymptotic freezing. Light from an object approaching the horizon becomes increasingly redshifted as time dilation intensifies. The photons struggle to climb out of the deepening gravitational well, losing energy as they ascend. From the perspective of a distant observer, the object appears to slow, dim, and freeze just above the horizon, never quite crossing. This is not an illusion. It is the genuine behavior of light in curved spacetime. The object's trajectory through time has diverged so completely from the observer's that the two can no longer share a common future. The observer will never witness the crossing, not because it does not happen, but because the information describing it cannot reach them. From the perspective of the infalling object, nothing unusual occurs at the horizon. They cross it smoothly, without encountering any barrier or discontinuity. Time, from their frame of reference, continues to flow normally. They experience no sudden change, no moment when they realize they have passed the point of no return. The horizon is not marked by any physical feature. It is simply a coordinate in spacetime defined by the geometry. But once crossed, the geometry ensures that every subsequent moment leads deeper inward. The singularity, once a distant abstraction, becomes an unavoidable future. This divergence between the experience of the infalling observer and the distant observers, the clearest manifestation of time's relativity near a black hole. The two observers do not merely disagree about the timing of events. They inhabit fundamentally different causal structures. For the distant observer, the infalling observer never crosses the horizon. For the infalling observer, they cross without incident and continue inward. Both perspectives are correct within their own frames of reference, but they cannot be reconciled into a single, universal timeline. The geometry does not allow it. Einstein's field equations predict all of this with precision. The Schwarzschild solution, the simplest exact solution to the field equations, describes the spacetime geometry around a non-rotating, uncharged black hole. The mathematics reveal the event horizon as the radius at which the curvature becomes so extreme that the roles of time and space exchange. Inside this radius, the radial coordinate, the one pointing toward or away from the center, becomes time-like. Outside, it is space-like. This exchange is not a quirk of coordinates. It reflects a genuine transformation in the structure of spacetime. Other solutions describe rotating black holes, charged black holes embedded in expanding universes. The details differ. The essential feature remains. The event horizon marks the boundary where spacetime curvature becomes so extreme that escape is geometrically impossible. The specific radius depends on the mass and properties of the black hole, but the principle is universal. Sufficient mass, concentrated in a small enough volume, will inevitably curve spacetime to the point where a horizon forms. And beyond the horizon lies the singularity, a point where the curvature becomes infinite, where the equations themselves break down. General relativity predicts its existence but cannot describe what happens there. The singularity is a boundary not just of spacetime but of the theory itself. It is the point where the fabric tears, where the geometric description fails, where new physics, perhaps quantum gravity, must take over. But the singularity is hidden. The event horizon shields it from the outside universe, ensuring that its pathologies do not contaminate the causal structure of the broader cosmos. This is the cosmic censorship hypothesis. Singularities, if they form, are always cloaked behind event horizons, invisible and causally disconnected from distant observers. Whether this hypothesis is universally true remains an open question, but it holds for every black hole solution discovered so far. The event horizon, then, is both a consequence and a shield. It is the inevitable result of extreme spacetime curvature, and it is the boundary that prevents that curvature from disrupting the rest of the universe. It is a threshold where time itself tilts irrevocably inward, where the future narrows to a single, unavoidable destination. And it is the edge of a region where the geometric language of general relativity describes a reality so alien to every day experience that human intuition can no longer follow, but the mathematics can. And the mathematics say this: mass does not rest on spacetime. Mass bends spacetime. And when the bending becomes extreme, time itself is dragged down into the geometry until the very concept of seconds begins to fail. And the horizon opens beneath you like a door into an unreachable future. Precision reveals what intuition cannot see. The slowing of time near massive objects is not a theoretical abstraction. It is a physical phenomenon, measurable with the right instruments, observable in the behavior of light and matter throughout the cosmos. But detecting it requires extraordinary precision. The effect is subtle at the scales accessible to human technology. Even near Earth, a planet of modest mass, the time dilation is measured in billions of a second. To confirm that time truly flows at different rates depending on gravitational depth, scientists needed clocks accurate enough to detect these minute discrepancies, devices that could tick with such consistency that a deviation of nanoseconds over days would register as a meaningful signal. Such clocks exist. They are called atomic clocks, and they measure time by counting the oscillations of atoms transitioning between energy states. These transitions occur at frequencies so stable that they define the second itself in the International System of Units. A cesium-133 atom, undisturbed, oscillates 9,192,631,770 times per second, with such regularity that the best atomic clocks lose less than 1 second over hundreds of millions of years. This consistency allows them to serve as exquisitely sensitive instruments for detecting gravitational time dilation. The first experimental confirmation came in 1971. In an experiment so straightforward in concept that it seems almost mundane in retrospect. Physicists Joseph Haffel and Richard Keating placed atomic clocks aboard commercial aircraft and flew them around the world, some eastward, some westward. When the clocks returned, they were compared to identical clocks that had remained stationary on the ground. The airborne clocks showed measurable differences. The eastward traveling clocks had lost time relative to the stationary ones. The westward traveling clocks had gained time. The differences were tiny, mere hundreds of nanoseconds, but they matched the predictions of general relativity with remarkable accuracy. The discrepancies arose from two effects. The first was velocity. The planes were moving relative to the Earth's surface, and special relativity predicts that moving clocks run slower. The second was altitude. The planes flew at higher elevations, farther from Earth's center of mass, where the gravitational field is weaker and time flows slightly faster. The combination of these effects produced the observed pattern. The experiment was crude by modern standards, but it provided direct, empirical evidence that time is not absolute. It flows at different rates depending on motion and gravity, exactly as Einstein's equations predict. Since then, the precision has improved by orders of magnitude. Modern atomic clocks are so sensitive that they can detect gravitational time dilation over differences in height of mere centimeters. Elevate a clock by 33 centimeters, roughly the height of a single stair. A step-end, it will tick measurably faster than a clock left on the ground. This is not error. This is time itself, flowing at a different rate in response to a change in gravitational potential so slight that it would be undetectable by any other means. These measurements confirm the predictions of general relativity with extraordinary fidelity. Time does not flow uniformly. It bends with spacetime, shaped by the presence of mass. And the deeper you are in a gravitational well, the slower your clock ticks relative to someone farther away. But atomic clocks on Earth only probe the weakest regimes of gravitational time dilation. To observe the effect in more extreme environments, scientists turn to astronomical observations. The cosmos provides natural laboratories where gravity is far stronger than anything achievable on Earth, and where the consequences of time dilation become dramatic. One of the clearest signatures comes from light itself. Photons climbing out of a gravitational well lose energy. This is not because they are absorbed or scattered, but because the geometry of spacetime through which they travel is curved. As a photon ascends, moving from a region of strong gravity to one of weaker gravity, its wavelength stretches, the light reddens, shifting toward longer wavelengths. This gravitational redshift is a direct consequence of time dilation. The photon is emitted at a particular frequency by an atom deep in the gravitational well, where time flows slowly. By the time the photon reaches an observer far away, where time flows faster, the frequency appears lower. The photon has not changed. The rate of time has. This effect is observable in the light from stars. The surface of a star is deep in its own gravitational well, and photons emitted there must climb out against the curvature of spacetime. The more massive the star, the stronger the gravity, and the more pronounced the redshift. White dwarf stellar remnants compressed to roughly the size of Earth, but with masses comparable to the Sun, exhibit measurable gravitational redshift in their spectra. The light from these objects is noticeably shifted toward the red compared to what would be expected from their composition and temperature alone. The shift is small, but it is consistent and predictable, matching the calculations derived from general relativity. Neutron stars provide even stronger evidence. These objects are the collapsed cores of massive stars, crushed by their own gravity to densities so extreme that a teaspoon of neutron star material would outweigh a mountain. The gravitational field at the surface of a neutron star is billions of times stronger than Earth's. Time dilation, there is not a subtle effect measured in nanoseconds. It is dramatic. A clock on the surface of a neutron star would run noticeably slower than one in free space far away. The gravitational redshift from neutron stars is significant. The order of tens of %10 has been measured in the light from these objects, confirming once again that time slows in the presence of extreme mass. Pulsars, a specific class of neutron stars that emit beams of radiation as they rotate, serve as particularly useful tools for testing general relativity. These objects spin with extraordinary regularity, their rotation periods stable to within microseconds over years. As the pulsar rotates, its beam sweeps across space like a lighthouse, and if Earth happens to lie in the path of that beam, we detect a pulse of radiation. The timing of these pulses can be measured with extraordinary precision, and any deviation from the expected pattern reveals information about the pulsar's environment. Some pulsars exist in binary systems, orbiting another star or compact object. As the pulsar moves through its orbit, it periodically descends deeper into the gravitational well of its companion, and then climbs back out. This motion produces a predictable pattern of time dilation. When the pulsar is deeper in the well, its clock, manifested in the regularity of its rotation, ticks more slowly relative to our clocks on Earth. The pulses arrive slightly later than expected. When the pulsar is farther from its companion, time flows faster, and the pulses arrive earlier. By tracking these variations over time, astronomers can map the gravitational field of the binary system with exquisite detail, confirming that time dilation occurs exactly as general relativity predicts. The most dramatic confirmation comes from objects even more extreme than neutron stars. Black holes, by their nature, are invisible. They emit no light, but their influence on surrounding matter and radiation betrays their presence. When a star orbits a black hole, its motion maps the curvature of spacetime in the vicinity of the event horizon. And when light passes near a black hole, it bends, redshifts, and distorts in ways that allow scientists to infer the properties of the black hole itself. One of the most striking examples comes from observations of the supermassive black hole at the center of our galaxy. Known as Sagittarius A*, this object has a mass equivalent to roughly 4 million suns, compressed into a region smaller than the orbit of Mercury. Stars orbit this black hole in elliptical paths, some passing extraordinarily close to the event horizon. By tracking the motion of these stars over decades, astronomers have measured their velocities, accelerations, and orbital parameters with stunning precision. One star in particular, designated S2, completes an orbit around Sagittarius A* every 16 years. At its closest approach, it swings to within 17 light hours of the black hole, traveling at speeds exceeding 5,000 kilometers per second, nearly 2% of the speed of light. At this distance, the gravitational field is immense, and the effects of general relativity become pronounced. Time dilation, both from velocity and from the intense gravity, slows the clock of any observer moving with the star. The light from S2, observed during its closest approach, shows a measurable gravitational redshift. The photons emitted by the star lose energy as they climb out of the black hole's gravitational well. The spectral lines shift toward longer wavelengths, exactly as general relativity predicts. The magnitude of the shift depends on how deep the star is in the gravitational well at any given moment. And the observed pattern matches the theoretical predictions with remarkable accuracy. This is direct evidence that time flows more slowly near the event horizon of a black hole than it does far away. But measuring the redshift is only one aspect of the observation. The shape of the star's orbit itself encodes information about the curvature of spacetime. In Newtonian gravity, an orbit is a fixed ellipse, unchanging over time. In general relativity, the ellipse itself rotates, a phenomenon called orbital precession. The curvature of spacetime near a massive object causes the orientation of the orbit to shift gradually with each revolution. For S2, this precession is measurable. The orbit does not close perfectly. Instead, it traces a rosette pattern, slowly rotating around the black hole. The rate of precession depends on the strength of the gravitational field, and the observed rate matches the predictions of general relativity, providing further confirmation that spacetime near a black hole is curved exactly as the theory describes. These observations are not limited to our own galaxy. Astronomers have detected similar patterns around black holes in other galaxies. In systems where stars or gas clouds orbit at relativistic speeds, their light stretched and distorted by the extreme gravity. In every case, the measurements aligned with the predictions of general relativity. Time slows, light redshifts, orbits precesses. The universe behaves as though spacetime is a flexible fabric bent by mass, and time is woven into that fabric, slowing wherever the curvature is strong. Even more direct evidence comes from the observation of light itself bending around black holes. In 2019, the Event Horizon Telescope collaboration released the first image of a black hole's event horizon specifically. The shape and size of the shadow encode information about the black hole's mass and the curvature of spacetime around it. The light forming the ring has traveled along geodesics through highly curved spacetime, some photons completing multiple loops around the black hole before reaching the telescope. The gravitational redshift is extreme. Photons emitted from the inner edge of the accretion disk, deep in the gravitational well, are redshifted dramatically by the time they escape. The side of the disk rotating toward us is blue shifted by the Doppler effect, while the side rotating away is redshifted. But underlying all of this is the gravitational redshift, a constant downward shift in frequency caused by the photons climbing out of the black hole's gravitational well. The image matches the simulations derived from general relativity with stunning precision. The size of the shadow, the brightness distribution of the ring, the asymmetry caused by the rotation of the accretion disk, all of these features are consistent with the predictions. The black hole is exactly where it should be, exactly the size it should be, surrounded by light that behaves exactly as it should in the presence of such extreme space-time curvature. This is not indirect evidence. This is a photograph of a region where time slows so dramatically that the boundary between time and space dissolves, where the future narrows to a single inward direction. Gravitational waves provide yet another window into the behavior of time near black holes. When two black holes orbit each other and eventually merge, they send ripples through space-time itself, distortions in the fabric that propagate outward at the speed of light. These waves were first detected in 2015 by the LIGO observatories, confirming a century-old prediction of general relativity. The signal from a black hole merger encodes information about the masses of the black holes, their spins, and the curvature of space-time in their vicinity. As the black holes spiral inward, they accelerate, moving faster and faster, deeper and deeper into each other's gravitational wells. Time dilation becomes increasingly severe. The frequency of the gravitational waves increases, a phenomenon called a chirp as the black holes approach merger. The final moments, when the black holes are separated by mere kilometers, involve space-time curvature so extreme that time itself becomes almost meaningless. The event horizons merge, forming a single, larger horizon, and the combined black hole settles into a stable configuration, radiating away the excess energy as gravitational waves. The detected waveforms match the predictions of numerical relativity computer simulations that solve Einstein's equations in these extreme regimes. The timing, the frequency evolution, the amplitude, all of it aligns with the theory. These detections are not just confirmations of gravitational waves. They are confirmations that time behaves as general relativity predicts, even in the most violent, chaotic, and extreme environments in the universe. Every measurement, from atomic clocks separated by centimeters to light escaping from black holes millions of light-years away, tells the same story. Time is not a fixed, universal constant. It is a dimension shaped by mass and motion, flowing at different rates depending on where you are and how you are moving. The slowing of time is not an artifact of clocks or an illusion of perception. It is a fundamental property of the universe, confirmed by observation, tested to extraordinary precision, and woven into the very fabric of space-time. Near a black hole, this property becomes undeniable. Time does not merely slow. It approaches a standstill, asymptotically freezing as you near the event horizon. From the perspective of a distant observer, an object falling toward a black hole never quite crosses. It slows, dims, fades, eternally suspended at the edge. This is not because of some barrier or resistance. 'Tis because time itself has been bent so severely that the future ceases to exist in the outward direction. The mathematics predict it, the observations confirm it, and the conclusion is inescapable. The event horizon is not just a boundary in space. It is a threshold where time itself begins to fail, where the clock stops ticking, and where the universe's most extreme geometry reveals the limits of temporal progression. The solution arrived in the midst of war. In 1915, Albert Einstein published his general theory of relativity, a set of equations describing how mass and energy curve the fabric of spacetime. The theory was elegant, profound, and maddeningly complex. The field equations, 10 interrelated differential equations, resisted straightforward solutions. Einstein himself could solve them only for highly idealized cases. The general problem, describing the curvature of spacetime around an arbitrary distribution of mass, seemed intractable. But within weeks of publication, a German physicist named Karl Schwarzschild found an exact solution. Schwarzschild was not working in a university laboratory or a quiet study. He was serving as a soldier on the Eastern Front during the First World War. Stationed in Russia, calculating artillery trajectories by day and pondering the structure of spacetime by night. Despite the chaos of war, despite the cold and the danger, He turned his attention to Einstein's equations and asked a deceptively simple question. What is the space-time geometry around a single, non-rotating, spherically symmetric mass? The answer came quickly. Schwarzschild derived a mathematical description of the curved spacetime surrounding such an objective solution so clean, so precise, that it seemed almost too simple. He sent his results to Einstein in December 1915. Einstein was astonished. He had not expected anyone to find an exact solution so soon, let alone under such circumstances. He presented Schwarzschild's work to the Prussian Academy of Sciences in January 1916, praising its elegance and significance. But embedded within the solution was something strange. The Schwarzschild metric, as it came to be called, described the curvature of spacetime at every point outside and inside a spherical mass. For most distances, the solution behaved as expected. Far from the mass, spacetime was nearly flat, and the metric approximated the familiar geometry of everyday experience. Closer to the mass, the curvature increased, and the predictions matched Newton's law of gravitation to high precision. But at a specific radius of distance determined solely by the mass of the object, the mathematics seemed to break down. This radius, now known as the Schwarzschild radius, appeared in the equations as a point where certain terms became infinite. The geometry exhibited what mathematicians call a singularity, a place where the normal rules fail. Where quantities diverge, where the solution ceases to make physical sense. For an object with the mass of the Sun, the Schwarzschild radius was about 3 kilometers. For Earth, it was less than a centimeter. These were distances far smaller than the actual size of the Sun or Earth. Buried deep within their interiors were the assumption of empty space around a point mass no longer held. So the singularity seemed irrelevant, a mathematical artifact with no physical consequence. Schwarzschild himself did not live to explore the implications. He contracted a rare autoimmune disease while serving on the front and died in May 1916. Less than 6 months after deriving his solution, he was 42 years old. His work survived him, a monument to clarity and insight born in the least likely of circumstances. For years, physicists dismissed the singularity at the Schwarzschild radius as a quirk of the coordinate system, a flaw in the way the equations were written. Not a feature of reality itself. Coordinates are arbitrary choices, labels imposed on spacetime to facilitate calculation. A singularity in the coordinates does not necessarily indicate a singularity in spacetime itself. Just as the apparent singularity at the North Pole on a globe is merely an artifact of latitude and longitude, not a physical anomaly. Surely, physicists thought the Schwarzschild radius was the same kind of illusion. Choose different coordinates and the singularity would vanish. The geometry would remain smooth and well-behaved. The solution would describe spacetime consistently at all distances. But the singularity did not vanish. Throughout the 1920s and 1930s, researchers investigated the Schwarzschild solution from every angle, reformulating it in different coordinate systems, probing its mathematical structure. Some singularities did disappear under transformation, revealed as coordinate artifacts. But the singularity at the Schwarzschild radius persisted in a different form. It was not a point where the curvature became infinite. The curvature there was large, but finite. Instead, it was a boundary in the causal structure of spacetime, a surface beyond which certain paths could not return. This realization emerged slowly, resisted at every step. The idea that a region of spacetime could be causally disconnected from the rest of the universe seemed absurd. It violated intuition. If you could travel to a place, you should be able to return. If light could reach a location, it should be able to escape. The notion of a one-way boundary, a threshold beyond which nothing, not matter, not light, not information could emerge, was too strange to accept without overwhelming evidence. The mathematics, however, were unambiguous. When Schwarzschild's solution was analyzed carefully, it revealed that spacetime inside the Schwarzschild radius had a fundamentally different structure than spacetime outside. The radial coordinate, which pointed outward in normal space, became time-like inside the radius. The time coordinate, which marked progression into the future outside the radius, became space-like inside. The two had exchanged roles. Inside the Schwarzschild radius, moving toward the center was not a spatial choice. It was a temporal inevitability, as unavoidable as moving from past to future. This was not a defect of the mathematics. It was a prediction. Einstein himself was skeptical. In 1939, he published a paper arguing that such a configuration could not form in nature. He reasoned that matter collapsing toward the Schwarzschild radius would encounter increasingly severe time dilation, slowing asymptotically as it approached the boundary. From the perspective of a distant observer, the collapse would take infinite time. The matter would never actually reach the Schwarzschild radius, let alone cross it. Therefore, he concluded, the region inside the radius was physically unreachable. A mathematical curiosity with no real-world counterpart. Others disagreed. In the same year, J. Robert Oppenheimer and his student Hartland Snyder published a paper analyzing the collapse of a massive star. They showed that while the collapse appears to freeze from the perspective of a distant observer, it proceeds normally from the perspective of the collapsing matter itself. The star does cross the Schwarzschild radius. It does not halt. It continues inward, compressing to ever higher densities, until the equations predict a true singularity at the center point of infinite curvature, where spacetime itself ceases to exist in any recognizable form. This was a radical claim. It suggested that stars, under the right conditions, could collapse entirely, vanishing from the observable universe and leaving behind only a gravitational imprinter region of curved spacetime from which nothing could escape. The boundary of this region was the Schwarzschild radius, and it marked a point of no return. The term black hole would not be coined for another 3 decades. In the interim, the concept existed in a state of theoretical limbo. Some physicists took it seriously. Others dismissed it as an unphysical extreme, a breakdown of the theory rather than a prediction. The problem was partly observational. No one had detected anything resembling such an object. Stars were well understood. Their life cycles, from formation to old age, followed predictable patterns governed by nuclear fusion and gravity. When a star exhausted its fuel, it either cooled into a white dwarf, exploded as a supernova, or in the most massive cases collapsed into a neutron star. These endpoints were exotic but comprehensible. The idea that a star could collapse beyond even a neutron star, compressing past the point where any known force could resist gravity, seemed unnecessary. Nature, it was assumed, would find a way to prevent such an outcome. The Second World War interrupted much of this theoretical work. Physics turned toward applied problems: radar, nuclear fission, the mechanics of explosions. The subtleties of general relativity and the fate of collapsing stars were set aside. Schwarzschild's solution remained a mathematical oddity, studied by a small community of specialists but largely ignored by the broader scientific world. The turning point came in the 1960s, driven by advances in both theory and observation. Mathematically, physicists developed new tools for analyzing the global structure of spacetime. Roger Penrose, in 1965, proved a theorem showing that under certain conditions, gravitational collapse must produce a singularity, a point where the curvature becomes infinite and the equations of general relativity break down. This was not a statement about coordinates or approximations. It was a rigorous result derived from the fundamental assumptions of the theory. If general relativity was correct, and if a sufficiently massive object collapsed, a singularity was inevitable. At the same time, astronomers began detecting objects that defied conventional explanation. Quasars, quasi-stellar radio sources were discovered in the early 1960s, emitting staggering amounts of energy from regions no larger than the solar system. The power output was so immense that no ordinary star or cluster of stars could account for it. The most plausible explanation involved matter falling into an extremely compact object. releasing gravitational energy as it spiraled inward. The calculations suggested that only an object compressed to or below its Schwarzschild radius could produce the observed luminosity. Around the same time, X-ray astronomy revealed binary star systems where one component was invisible but exerted a powerful gravitational influence on its companion. Gas stripped from the visible star spiraled into the unseen partner, heating to millions of degrees and emitting X-rays in the process. The mass of the invisible object, inferred from the orbital dynamics, exceeded the maximum mass a neutron star could sustain. There was no known form of matter that could resist collapse under such conditions. The only remaining possibility was that the object had already collapsed, that it was a region of spacetime bounded by an event horizon, visible only through its gravitational effects and the radiation emitted by matter falling toward it. By the late 1960s, the theoretical framework had solidified. John Archibald Wheeler, a physicist with a talent for vivid language, began using the term black hole to describe these objects. The name captured the essential features: a region of space from which nothing could escape, appearing black because no light could emerge. The term was initially informal, almost whimsical, but it took hold. Within a few years, black hole became the standard nomenclature, replacing earlier awkward phrases like frozen star or collapsed object. The acceptance of black holes as real physical entities represented a profound shift in scientific thinking. For decades, the Schwarzschild radius had been treated as a theoretical boundary, a mathematical abstraction that nature would somehow avoid. But the evidence accumulated. The observations demanded an explanation. And the only explanation consistent with general relativity was that stars could collapse past the point of no return, forming regions of spacetime from which escape was impossible. The event horizon, once dismissed as a coordinate artifact, was recognized as a genuine physical boundary. It was not a surface in the ordinary sense, no material membrane, no barrier that could be touched or seen. It was a threshold in the geometry of spacetime, defined by the property that any future directed path crossing it led inevitably inward. Light emitted from inside the horizon could not reach the outside. Information could not escape. The interior was causally disconnected from the exterior, severed from the observable universe by the curvature of spacetime itself. This realization had profound implications. It meant that the universe contained regions that were, in principle, unreachable and unknowable. Once something crossed the event horizon, it was lost to the outside world forever. No signal could return. No rescue was possible. The boundary was absolute, enforced not by any physical barrier, but by the structure of time itself. Further theoretical work revealed additional features. Roy Kerr, in 1963, found a solution to Einstein's equations, describing a rotating black hole. The Kerr solution was more complex than Schwarzschild's, involving frame-dragging effects where the rotation of the black hole twisted spacetime around it, pulling everything nearby into a swirling motion. But it too contained an event horizon, a boundary beyond which escape was impossible. Rotating black holes, it turned out, were not just theoretical possibilities, but likely the norm. Most stars rotate, and when they collapse, their angular momentum is preserved, spinning the resulting black hole to extraordinary speeds. The study of these solutions revealed the diversity of black holes. They could be small or large, spinning or static, electrically charged or neutral. But all shared the defining feature, an event horizon marking the point where time is experienced by distant observers ground to a halt. The Schwarzschild breakthrough had opened a door to an entire class of objects, each representing an extreme distortion of spacetime, each demonstrating that the universe permitted regions where the normal rules of cause and effect were fundamentally altered. And the breakthrough had come from a soldier on the Eastern Front, calculating by candlelight, solving equations while the world burned around him. Schwarzschild had not known what he had found. He had seen a mathematical structure, elegant and precise, describing the curvature of spacetime around a mass. He had noted the singularity, puzzled over it briefly, and moved on. He could not have known that his solution would become the foundation for understanding the most extreme objects in the cosmos. He could not have known that the radius bearing his name would mark the boundary where time itself fails, where the future becomes inescapable, where the clock stops and the universe divides into the observable and the forever hidden. But the mathematics were there, waiting. And once the scientific community accepted what the equations were saying, the event horizon ceased to be a curiosity and became a certainty, a real, physical threshold existing in nature, predicted by theory, confirmed by observation, and inevitable whenever sufficient mass collapses into sufficient density. The frozen star was no longer frozen. It had crossed the boundary. And the boundary remained, a permanent scar in spacetime, a place where time slows to nothing and the journey inward becomes a journey with no return. The approach is layered, like descending through zones of increasing strangeness. A black hole is not a singular point floating in empty space. It is a complex architecture, a nested series of regions where the rules of physics shift progressively from the familiar to the incomprehensible. At great distances, the black hole appears almost mundane, a gravitational influence like any other massive object, bending light, tugging on nearby matter, exerting its pull according to the same principles that govern planets and stars. But as you move closer, the character of spacetime changes. The curvature steepens, time slows. Light bends more sharply. And eventually, you cross invisible boundaries where the environment transitions into regimes that have no analog in ordinary experience. The outermost visible feature is often the accretion disk. Matter does not fall directly into a black hole. It spirals. Gas, dust, fragments of stars, anything drawn toward the black hole by gravity carries angular momentum, a measure of its rotation around the central mass. This momentum cannot simply disappear. As the material falls inward, it begins to orbit, forming a flattened disk that encircles the black hole like the rings of Saturn, but vastly larger and incomparably more violent. The accretion disk is a place of extremes. Friction between particles orbiting at different speeds converts gravitational potential energy into heat. The inner regions of the disk, where the orbital velocities approach a significant fraction of the speed of light, reach temperatures of millions of degrees. The material glows, radiating across the electromagnetic spectrum, radio waves, visible light, ultraviolet, X-rays. For certain black holes, particularly those feeding actively on nearby stars or gas clouds, the accretion disk becomes the brightest object in the region, outshining entire galaxies. The black hole itself remains invisible, but its presence is betrayed by the furious luminosity of the matter swirling toward it. The disk is not uniform. Turbulence, magnetic fields, and instabilities create complex patterns, bright spots, jets, flares. Matter does not simply spiral smoothly inward. It clumps, collides, heats unevenly. Some of it is flung outward in powerful jets that shoot perpendicular to the disk, accelerated to relativistic speeds by magnetic fields twisted and amplified by the rotation of the black hole. These jets can extend for thousands of light years, carrying energy far beyond the immediate vicinity of the event horizon, broadcasting the presence of the black hole across cosmic distances. Closer still lies a region of peculiar geometry known as the photon sphere. Light, under normal circumstances, travels in straight lines. But near a black hole, space-time is so curved that the paths of photons bend. At a specific distance, precisely 1.5 times the Schwarzschild radius for a non-rotating black hole, the curvature is such that light can orbit. A photon traveling tangentially at this radius will circle the black hole indefinitely, trapped in a closed loop by the geometry of spacetime. This is the photon sphere, and it is as strange as it sounds. If you could somehow position yourself at this radius and look around, you would see not just the accretion disk and the stars beyond, but also the back of your own head. Light emitted from the back of your skull would curve around the black hole and return to your eyes from the front. You would see infinite regressing images of yourself, each one more redshifted and dimmed than the last, as light completed multiple orbits before reaching you. The photon sphere is unstable. Any slight perturbation, a nudge inward or outward on the photon's orbit decays. It moves inward, it spirals toward the event horizon and is lost. If it moves outward, it escapes to infinity. There is no stable middle ground. Light cannot rest here. It is a boundary of razor-thin precision, a shell of captured radiation surrounding the black hole like a luminous ghost. Below the photon sphere, the environment changes fundamentally. The gravitational pull becomes so strong that escape is no longer merely difficult, it is increasingly constrained. Imagine standing on this surface and firing a rocket. No matter how powerful the engine, no matter what direction you point, you cannot escape unless you aim within an increasingly narrow cone pointing away from the black hole. As you descend closer to the event horizon, this cone shrinks. The range of directions that lead to freedom narrows. At the event horizon, the cone closes entirely. There are no outward directions left. Every path leads inward. This is not a metaphor. The geometry of spacetime has physically eliminated the possibility of outward motion. The future, which outside the black hole spreads in all spatial directions, has collapsed to a single spatial direction inside. The event horizon marks the threshold where this collapse is complete. The size of the event horizon depends entirely on the black hole's mass. For a stellar mass black hole, one formed from the collapse of a massive star, the Schwarzschild radius is typically a few kilometers. The entire event horizon, a sphere defined by this radius, would fit comfortably inside a small city. These black holes are compact, fierce, unforgiving. The tidal forces near the horizon are catastrophic. An object falling toward such a black hole would be stretched and compressed by the difference in gravitational pull across its length. A process known as spaghettification. Long before crossing the horizon, the object would be torn apart, ripped into streams of atoms by forces no material structure could resist. But not all black holes are small. Supermassive black holes, found at the centers of galaxies, have masses millions or billions of times that of the Sun. Their event horizons are correspondingly vast. The supermassive black hole at the center of the Milky Way has a Schwarzschild radius of roughly 12 million kilometers, about 17 times the radius of the Sun. The event horizon of the black hole in M87, the one imaged by the Event Horizon Telescope, is larger still, with a radius comparable to the entire solar system. At this scale, the environment near the horizon is surprisingly gentle. The tidal forces, which depend on the gradient of the gravitational field, are inversely proportional to the square of the black hole's mass. A supermassive black hole stretches spacetime so gradually that an object crossing the event horizon might not even notice. There would be no violent tearing, no sudden catastrophe. The geometry would be smooth, the curvature mild. An astronaut could cross the threshold and, for a brief time, experience nothing unusual. Only later, as they continued inward and the curvature intensified, would the tidal forces grow lethal. This counterintuitive fact that larger black holes are gentler at the horizon underscores the geometric nature of the boundary. The event horizon is not defined by the strength of gravity in the conventional sense. It is defined by the structure of spacetime, by the point where the causal future narrows to a single direction. For a small black hole, this point lies deep within a region of violent curvature. For a large black hole, it can lie in a region that is, by comparison, calm. The horizon itself has no physical substance. If you were falling toward a black hole, you would not encounter a wall, a surface, a barrier of any kind. There is no membrane marking the boundary, no change in temperature or density, no sudden transition. The event horizon is a coordinate in spacetime, defined mathematically as the surface where the escape velocity equals the speed of light. Cross it, and you have entered a region from which no future path leads outward. But the crossing itself is smooth, unremarkable, imperceptible to the infalling observer. This invisibility makes the event horizon both profoundly simple and deeply unsettling. It is the ultimate point of no return, yet it announces itself with no warning. You cannot see it approaching. You cannot feel it as you cross. There is no moment when you realize, viscerally, that you have passed the threshold. Only later, when you try to send a signal outward and realize that every photon you emit is dragged back inward, would the truth become clear? By then, it is far too late. From the outside, however, the horizon is visible not as an object, but as an absence. Light from the accretion disk, from distant stars, from the cosmic microwave background, all of it bends around the black hole. Some of this light escapes, carrying information about the surrounding environment. But light originating from inside the horizon cannot escape. The region within appears as a perfect circle of darkness, a shadow cast not by an obstruction, but by the geometry of spacetime itself. This shadow is larger than the event horizon. It is bounded by the photon sphere, the region where light orbits the black hole before either escaping or falling in. The size of the shadow depends on the black hole's mass and spin. But for a non-rotating black hole, it is precisely 2.6 times the Schwarzschild radius. The Event Horizon Telescope image of M87 captured this shadow, a dark circle silhouetted against the bright emission from the accretion disk. The darkness is the event horizon, made visible by the light it refuses to release. The architecture becomes more complex for rotating black holes. When a black hole spins, it drags spacetime along with it, a phenomenon called frame dragging. Near the event horizon, this effect is extreme. Space itself is pulled into a rotating motion, forced to swirl around the black hole like water circling a drain. An object hovering just outside the horizon would find itself carried along, rotating with the black hole whether it wanted to or not. No amount of thrust could keep it stationary relative to distant stars. The rotation of spacetime is inescapable. This dragged region is called the ergosphere, and it extends slightly beyond the event horizon. Within the ergosphere, spacetime rotates so rapidly that even light cannot remain stationary. Every photon is pulled into a rotating trajectory, forced to orbit the black hole along with the dragged spacetime. But unlike the event horizon, the boundary of the ergosphere is not a point of no return. Escape from the ergosphere is still possible, though it requires moving in the direction of the rotation. This asymmetry creates the potential for extracting energy from a rotating black hole, a process known as the Penrose mechanism, where particles or light can gain energy at the expense of the black hole's rotation. The geometry of a rotating black hole is richer than that of a static one. The event horizon is no longer a perfect sphere, but an oblate spheroid, flattened by the centrifugal effects of rotation. The singularity at the center is no longer a point, but a ring, a circle of infinite curvature spinning in the equatorial plane. The structure is more complex, the mathematics more intricate, but the essential feature remains. The event horizon is a boundary beyond which the future points inward. And time, as measured by distant observers, slows to a halt. Scale matters in ways that extend beyond the tidal forces. A stellar mass black hole, with an event horizon only kilometers across, exerts its influence over a relatively small region. Its gravitational reach is significant, but localized. A supermassive black hole, by contrast, dominates the center of its galaxy. Its gravitational field shapes the orbits of millions of stars, channels gas into the accretion disk, anchors the galactic core. The event horizon itself, though vast, represents only a tiny fraction of the black hole's sphere of influence. Yet, despite their differences in size and environment, all black holes share the same fundamental property. They are regions of spacetime bounded by an event horizon, a threshold where the geometry becomes so curved that time and space exchange roles, where the future collapses to a single inward direction, where escape becomes not difficult but impossible. The size determines the details, the tidal forces, the temperature of the accretion disk, the duration of the fall from horizon to singularity, but the principle is universal. And this universality points to something profound about the nature of time itself. The event horizon is not imposed by any external force. It is not maintained by a field or a substance. It emerges purely from the geometry of spacetime, from the way mass curves the fabric of reality. Time slows at the horizon because the curvature is such that the temporal dimension tilts inward, that the coordinate we call future aligns with the coordinate we call toward the center. The clock stops not because it breaks, but because time itself has been bent into a shape where forward progression leads inevitably inward. This architecture, the accretion disk, the photon sphere, the ergosphere, the event horizon, forms a landscape of increasing entrapment. Each layer represents a deeper commitment to the black hole's pull, a narrowing of possible futures, a progressive elimination of escape routes. At the outermost edges, escape is easy. Closer in, it requires increasing energy. At the photon sphere, even light must be aimed precisely to escape. At the event horizon, no aim is sufficient. The boundary is absolute. And beyond the horizon lies a region that no information can ever describe to the outside universe. Whatever happens there is hidden, not by secrecy or obscurity, but by the structure of causality itself. The interior is severed from the exterior, separated by a one-way membrane woven from the geometry of space-time. The event horizon is the gatekeeper, and it allows passage in only one direction. This is the abyss, not a hole in the ordinary sense, but a depth in the fabric of reality where time itself fails, where the clock stops ticking for those who watch from afar, where the future becomes a fixed destination rather than an open possibility. It is a structure predicted by mathematics, confirmed by observation, and woven into the cosmos at every scale, from the remnants of dead stars to the anchors of galaxies. And it stands as the ultimate boundary between the knowable and the forever unreachable, a threshold where the architecture of spacetime bends so severely that the path forward in time becomes indistinguishable from the path inward in space. And the journey continues into silence. Light near the horizon begins to struggle. Photons are the universe's messengers, carrying information from one point to another at the maximum speed permitted by the structure of space-time. In empty, flat space, they travel effortlessly, covering vast distances without delay. But near a black hole, the geometry through which they move is no longer flat. Space-time is curved, and that curvature affects the photon's journey in ways that become increasingly severe as the event horizon approaches. Consider a photon emitted from the surface of an object falling toward a black hole. The photon is emitted upward, away from the black hole, attempting to escape to a distant observer. In flat spacetime, this would be straightforward. The photon would travel outward at the speed of light, reaching the observer in a time determined simply by the distance. But near a black hole, the photon must climb out of a gravitational well, and this climb costs energy. The photon does not slow down. It always travels at the speed of light, locally. But as it ascends through the curved space-time, its wavelength stretches. The energy of a photon is inversely proportional to its wavelength, so as the wavelength increases, the energy decreases. The photon redshifts, shifting toward longer wavelengths. Toward the red end of the visible spectrum, and beyond, did the infrared, the microwave, the radio. The deeper in the gravitational well the photon originates, the more it must climb, and the more it redshifts. This redshift is measurable. Photons emitted from the surface of a white dwarf are slightly redshifted compared to identical photons emitted in free space. Photons from a neutron star are redshifted more. Photons from the vicinity of a black hole's event horizon are redshifted so dramatically that they become almost undetectable. The shift is not gradual, but asymptotic, growing without bound as the emission point approaches the horizon. From the perspective of a distant observer, this redshift has a temporal interpretation. The wavelength of light is related to the frequency of oscillation, and frequency is a measure of time. A photon that oscillates slowly with a long wavelength appears to have been emitted from a region where time is running slowly. The redshift of the photon encodes the time dilation of its source. As an object falls toward the event horizon, the photons it emits are progressively more redshifted. The light grows dimmer, not because the object is intrinsically fading, but because the photons are losing energy as they climb out of the deepening gravitational well. The color shifts from white to red, from red to infrared. From infrared to wavelengths so long they are invisible to any conventional detector. The object appears to slow down, its motion becoming sluggish as the photons take longer and longer to escape. The image freezes, dimming and reddening, locked in a moment that never quite completes. This is the frozen star paradox. From the perspective of the distant observer, the falling object never crosses the event horizon. It approaches asymptotically, slowing to a halt just above the boundary, its final photons stretched to infinite wavelength, carrying information about a moment that is eternally prolonged. The object does not vanish. It lingers, fading into invisibility but never truly disappearing, suspended at the edge of the black hole for all time. But from the perspective of the falling object, nothing unusual happens. The object crosses the event horizon smoothly, without encountering any barrier, without slowing, without experiencing the redshift that the distant observer sees. Time for the falling object flows normally. The horizon passes beneath it like any other coordinate in spacetime. The object continues inward, unaware that to the outside universe it has become frozen, a ghost image lingering forever at the threshold. This divergence is not a paradox in the sense of a logical contradiction. It is a consequence of the relativity of time. The distant observer and the falling object do not share a common timeline. Their presence have separated, diverging as the curvature of spacetime becomes extreme. What is simultaneous for one is not simultaneous for the other. What is future for one is unreachable for the other. The event horizon marks the boundary where this separation becomes absolute. The mathematics describe this with precision. The Schwarzschild metric contains a coordinate called Schwarzschild time, which measures time as experienced by a stationary observer far from the black hole. In this coordinate system, the time required for an object to reach the event horizon is infinite. The object's trajectory approaches the horizon asymptotically, never quite arriving. This is not an artifact of poor mathematics. It is a genuine feature of the geometry, reflecting the fact that the distant observer's notion of time does not extend smoothly across the event horizon. But there are other coordinate systems. The Eddington-Finkelstein coordinates, for example, describe the same space-time geometry but use a time coordinate that flows smoothly through the event horizon. In this system, the infalling object crosses the horizon in a finite amount of proper time, the time measured by a clock carried along with the object. The two descriptions are both correct, each valid within its own frame of reference, but they cannot be unified into a single narrative that spans both perspectives. This is the essential strangeness of the event horizon. It is a boundary in the causal structure of spacetime, a surface where different observers' timelines diverge irreconcilably. For the distant observer, the horizon is a place where time stops, where events are stretched into an eternal present. For the infalling observer, the horizon is an ordinary point in spacetime, crossed without incident. Both are true. Both are consequences of the same underlying geometry. The photons emitted from near the horizon tell this story in visual form. Imagine watching a clock fall toward a black hole. The clock ticks normally at first, each second marked by a flash of light. As the clock descends, the flashes arrive at increasingly long intervals. The gravitational time dilation slows the clock relative to your frame of reference. The intervals between flashes grow longer: 2 seconds, 10 seconds, a minute, an hour. As the clock approaches the event horizon, the intervals stretch to days, then years, then centuries. The final flash, emitted just as the clock reaches the horizon, takes infinite time to arrive. You will never see the clock cross. You will only see it approach, dimming and slowing, asymptotically frozen at the edge. But the clock itself experiences no such delay. It ticks at a constant rate, 1 second per second, according to its own internal mechanism. It crosses the event horizon and continues ticking, oblivious to the fact that its signals can no longer reach you. The information encoded in those final photons becomes infinitely diluted. Each photon emitted from closer to the horizon carries less energy, stretched by the gravitational redshift to longer and longer wavelengths. But wavelength is not merely a property of the photon, it is a measure of the spatial extent of the electromagnetic wave. A photon with a wavelength of 1 meter occupies, in some sense, a meter of space. A photon redshifted to a wavelength of a kilometer occupies a kilometer. As the emission point approaches the event horizon, the wavelength approaches infinity. The photon is stretched across the entire observable universe, its energy diluted to the point of undetectability. This stretching has profound implications for information. Every detail about the falling object, its shape, its composition, the precise moment it crosses the horizon is encoded in the light it emits. But as the photons redshift toward infinite wavelength, the information they carry becomes spread over infinite time and infinite space. From the perspective of the distant observer, the information never fully arrives. It trickles in asymptotically, each successive bit taking exponentially longer to reach the observer until the rate of information transfer approaches zero. This creates a peculiar situation. The object has crossed the horizon from its own perspective, completing the journey in finite time. But from the outside perspective, the information describing that crossing is delayed indefinitely. The universe, as seen by the distant observer, retains a fading imprint of the object suspended at the horizon, a ghost image that persists even though the object itself has moved on. This ghostly persistence is not merely theoretical, it has measurable consequences. When matter falls into a black hole, it carries with it certain properties: mass, charge, angular momentum. These properties affect the spacetime geometry outside the event horizon. The black hole's mass increases. Its gravitational field strengthens. If the infalling matter carries electric charge, the black hole becomes charged. If it carries angular momentum, the black hole begins to spin. These changes occur on timescales that are finite and measurable from the outside. But the information about what specifically fell in, whether it was hydrogen or iron, whether it was structured as a star or a diffuse cloud, whether it had entropy or organizations lost, the black hole retains only the most basic properties: mass, charge, and spin. Everything else is erased, or more precisely, hidden behind the event horizon, where it cannot influence the outside universe. This erasure is known as the no-hair theorem, a somewhat whimsical name for a profound result. Black holes, according to classical general relativity, have no distinguishing features beyond these three quantities. All other information is either lost or inaccessible. The photons emitted during the infall carry the final traces of that information. But they are stretched and redshifted to the point where recovery becomes impossible in practice. The information is not destroyed in the classical sense; it remains encoded in the geometry of spacetime. But it is rendered unreachable, smeared across the horizon in a form that cannot be reassembled into a coherent picture. This raises deep questions about the nature of information in physics. In quantum mechanics, information is supposed to be conserved. The state of a system evolves deterministically, and in principle, if you know the present state completely, you can reconstruct the past and predict the future. But a black hole seems to violate this principle. Information falls in, and from the outside perspective, it never comes back out. The black hole evaporates eventually through Hawking radiation, a quantum process that causes black holes to emit particles and slowly lose mass. But the radiation appears to be thermal, carrying no information about what fell in. The information seems to have been destroyed, a result that conflicts with fundamental principles of quantum mechanics. This is the black hole information paradox, and it remains one of the central unsolved problems in theoretical physics. The resolution may require a theory of quantum gravity, a framework that unifies general relativity and quantum mechanics. Such a theory does not yet exist in complete form, though candidates like string theory and loop quantum gravity offer hints. The paradox suggests that the classical picture of the event horizon, a smooth, featureless boundary where nothing unusual happens locally, may be incomplete. Quantum effects near the horizon may alter the geometry in subtle ways, encoding information in structures that classical relativity cannot describe. But the classical picture remains accurate for the phenomena we can observe. The photon's redshift. The object appears to freeze. The information becomes inaccessible. These are consequences of the geometry of spacetime, confirmed by observation, independent of quantum corrections. The event horizon is a place where light stalls, where the wavelength of emitted radiation stretches toward infinity, where the messages from the falling object take infinite time to fully arrive. And this stalling is not limited to light. It applies to all signals, all forms of information. Gravitational waves, ripples in spacetime itself, also redshift as they climb out of a gravitational well. A gravitational wave emitted from near the horizon would be stretched to enormous wavelengths, its frequency dropping, its energy diluting, until it became indistinguishable from the background noise of spacetime fluctuations. Neutrinos, nearly massless particles that interact weakly with matter, would also be affected. They would not redshift in the same way as photons. Neutrinos have mass and do not travel precisely at the speed of light, but they would still experience time dilation, their clocks slowing as they climbed out of the gravitational well. Every form of communication, every carrier of information, is subject to the same constraint. The event horizon is a boundary beyond which signals cannot escape, not because they are blocked by a barrier, but because the geometry of spacetime forbids outward paths. Photons emitted from inside the horizon are aimed outward, traveling at the speed of light in their local frame, but the curvature of spacetime is so extreme that outward has ceased to be a direction that leads away from the black hole. The photons spiral inward, despite their outward aim, dragged by the geometry toward the singularity. And photons emitted from precisely at the horizon occupy a liminal state. They hover there, neither escaping nor falling, locked in place by the perfect balance between their outward velocity and the inward curvature of spacetime. These photons form a surface of trapped light, a shell of radiation suspended at the boundary, visible to no one, existing in a state of eternal transit. This is why the event horizon appears as a surface of infinite redshift. The photons trying to escape from exactly the horizon are stretched to infinite wavelength, their frequency dropping to zero, their energy vanishing. They are light that no longer propagates, frozen in the geometry, neither inside nor outside, but exactly on the boundary. For photons emitted from just inside the horizon, the situation is even more extreme. They are dragged inward, unable to make any progress outward, condemned to fall toward the singularity regardless of their initial direction. The stalling of the photon is the visual signature of the event horizon. It is the phenomenon that makes the boundary observable, even though the boundary itself is immaterial. The redshift grows without limit. The light fades to invisibility. The information smears across infinite time, and the distant observer is left watching an object that appears to hang forever at the edge of the abyss, dimming and reddening, its final moments stretched into eternity, its crossing forever postponed. But the crossing happens. The object passes through, experiences the horizon as an ordinary moment, and continues inward. The photons it emits afterward are trapped, unable to escape, carrying information that will never reach the outside. The timeline has split. The outside universe will never know what happens beyond the threshold. The photons that could tell the story are stalled at the horizon, stretched to infinite wavelength, carrying messages that take infinite time to deliver, encoding a future that is unreachable from the outside. This is the final evidence. The clock for the outside universe has stopped. Not because time is ended, but because the geometry of spacetime has bent so severely that the future of the falling object no longer intersects with the future of the distant observer. The photon, the ultimate messenger, has been defeated not by distance, not by obstruction, but by the curvature of time itself, which has tilted so far inward that escape is no longer a possibility. And the light that should carry the story outward is instead held captive at the boundary, frozen in an eternal red glow that fades into darkness and silence. The horizon remembers everything that falls in. This is not metaphor. It is a prediction of physics, emerging from the collision of thermodynamics, quantum mechanics, and general relativity. When matter crosses the event horizon, it does not simply disappear from the universe. It leaves an imprint or record encoded on the surface of the horizon itself. This encoding is subtle, invisible to classical observation, but it suggests something profound about the architecture of reality. That the three-dimensional volume of space may be less fundamental than the two-dimensional surfaces that bound it. The first hint came from thermodynamics. In the 1970s, physicists studying black holes noticed a curious parallel between the laws governing black holes and the laws governing entropy. Entropy is a measure of disorder, a quantity that always increases in isolated systems according to the second law of thermodynamics. When you break a glass, burn fuel, or mix hot and cold water, entropy rises. The universe trends toward disorder, and this trend is irreversible. Black holes seem to violate this principle. Imagine throwing a box of highly organized matter, a book, a crystal, a living organism into a black hole. The matter crosses the horizon and vanishes from the observable universe. Its entropy, which was previously counted as part of the universe's total, seems to disappear. The total entropy of the universe appears to decrease, violating the second law. Jacob Bekenstein proposed a solution. He suggested that black holes themselves possess entropy, and that this entropy is proportional to the surface area of the event horizon, not the volume enclosed. When matter falls into a black hole, its entropy is transferred to the horizon, increasing the black hole's entropy and preserving the second law. The horizon, in effect, stores the information that fell in encoded somehow on its two-dimensional surface. This was a radical idea. Entropy is usually associated with the number of possible microscopic states a system can occupy. A gas in a box has high entropy because the molecules can be arranged in many different configurations that look macroscopically the same. But a black hole, according to classical general relativity, has no internal structure. It is defined entirely by its mass, charge, and spin. There should be no microscopic states to count, no hidden configurations, no entropy at all. Yet Bekenstein's proposal made mathematical sense. The area of the event horizon increases whenever matter or energy falls in, and it can never decrease, a property known as the area theorem, proven by Stephen Hawking. This behavior mirrors the second law of thermodynamics, where entropy increases and never decreases. If the area of the horizon is proportional to entropy, then the second law is preserved even when matter crosses into the black hole. Hawking took the idea further. Using quantum field theory in curved spacetime, he showed that black holes are not entirely black. They emit radiation, thermal radiation, with a temperature inversely proportional to the black hole's mass. This radiation, now called Hawking radiation, causes the black hole to lose mass over time, evaporating slowly. The temperature of the radiation is extraordinarily low for astrophysical black holes, far colder than the cosmic microwave background, making the effect impossible to observe directly. But the theoretical prediction is clear. Black holes have a temperature, and where there is temperature, there is entropy. The entropy of a black hole, according to the Bekenstein-Hawking formula, is proportional to the area of the event horizon measured in units of the Planck length, the fundamental length scale, where quantum gravity becomes important. The formula is precise. Entropy equals 1/4 of the horizon area divided by the Planck length squared. This gives an astronomically large number even for relatively small black holes. A black hole with the mass of the Sun has an entropy exceeding 10 to the power of 77, far greater than the entropy of the Sun itself. This entropy must correspond to something. If a black hole has entropy, it must have a vast number of internal microstates configurations that are indistinguishable from the outside but differ at a microscopic level. Classical general relativity cannot describe these states. The black hole is smooth, featureless, defined only by mass, charge, and spin. The microstates must be quantum in nature, encoded somehow in the structure of the event horizon. But how can a three-dimensional volume of space, potentially containing collapsed stars, gas, and radiation, be encoded on a two-dimensional surface? The answer lies in the holographic principle, one of the most startling insights in modern theoretical physics. The principle emerged from efforts to understand black hole entropy and the information paradox. If information is conserved in quantum mechanics, then the information about everything that falls into a black hole must be preserved somewhere. It cannot simply vanish. Bekenstein's entropy formula suggested that the information is stored on the horizon, but the mechanism was unclear. How could the horizon, a surface, contain all the information of a volume? Gerard T. Hooft and later Leonard Susskind proposed that this is not a special property of black holes, but a general feature of spacetime. They suggested that the information contained in any region of space can be fully encoded on the boundary of that region. The three-dimensional reality we experience, the depth, the volume, the interiors, in some sense redundant. All the information is present on the surface. Much like a hologram encodes a three-dimensional image on a two-dimensional film. This is the holographic principle, and it implies that the universe may be fundamentally two-dimensional, with the third dimension emerging as a kind of projection. The physics taking place in a volume of space can be equivalently described by a theory operating on the boundary of that volume. The interior and the surface are dual descriptions of the same reality. Evidence for the holographic principle comes from string theory, a candidate for a theory of quantum gravity. In certain formulations, string theory admits a precise mathematical correspondence between a theory of gravity in a hard-dimensional space and a quantum field theory without gravity in one fewer dimension. This correspondence, known as the ADS-CFT duality, shows that the holographic principle is not merely a metaphor, but a rigorous equivalence. The gravitational physics in the interior can be fully reconstructed from the boundary theory and vice versa. For black holes, the holographic principle offers a resolution to the information paradox. When matter falls into a black hole, the information about that matter is not lost. It is encoded on the event horizon in a scrambled, highly entangled form. An outside observer, in principle, could recover the information by analyzing the Hawking radiation emitted as the black hole evaporates. The radiation is not perfectly thermal. It carries subtle correlations, imprinted by the quantum state of the horizon, that encode everything that fell in. The encoding is maximally efficient. The area of the horizon, measured in Planck units, gives the maximum number of bits of information that can be stored. This is a universal bound, not limited to black holes. Any region of space has a maximum entropy proportional to the area of its boundary, not its volume. If you try to pack more information into a region than this limit allows, the region collapses into a black hole, and the information is redistributed onto the newly formed horizon. This revelation transforms the meaning of the frozen horizon. When an object falls toward a black hole and appears to freeze at the edge, the image is not merely an optical illusion created by extreme time dilation. It is a reflection of a deeper truth. The information describing that object is being encoded onto the two-dimensional surface of the event horizon. The freezing is the visible signature of this encoding process. a consequence of the fact that the horizon acts as a repository for all the information that crosses it. From the perspective of the distant observer, the object never quite crosses. It slows, reddens, and fades, its final state smeared across the horizon. This frozen image is not a distortion or a trick of light. It is the holographic encoding of the object, preserved on the boundary. The three-dimensional object has been mapped onto a two-dimensional surface, and what the distant observer sees is the last light emitted before this mapping becomes complete. The information is scrambled beyond recognition. The details of the object's internal structure, its composition, the arrangement of its atoms, all of this is encoded in a form that is hopelessly entangled with the quantum state of the horizon. An outside observer cannot simply look at the horizon and read off what fell in. The encoding is encrypted by the extreme complexity of the horizon's quantum state, distributed across Planck scale degrees of freedom that are far too small and numerous to access individually. But the information is there. It persists, even as the object itself has crossed the horizon from its own perspective and continued inward. The two perspectives, inside and outside, describe different aspects of the same reality. The infalling observer experiences crossing the horizon and moving toward the singularity. The distant observer sees the information encoded on the horizon, preserved in a form that will eventually be released through Hawking radiation as the black hole evaporates. This duality is at the heart of the holographic principle. The interior of the black hole and the surface of the horizon are not independent regions. They are complementary descriptions, each valid from a particular perspective, but ultimately encoding the same information. The observer who falls in experiences one narrative. The observer who stays outside experiences another. Both are real. Both are consistent with the laws of physics, but they cannot be naively combined into a single objective story. The holographic principle suggests that this duality extends beyond black holes. Any region of space, bounded by an imaginary surface, can be described holographically. The physics inside the region, the particles, fields, forces, interactions can be equivalently described by a theory on the boundary. The boundary does not cause the interior. It is not prior to it. Rather, the two are different representations of the same underlying reality. This has profound implications for the nature of space itself. If the holographic principle is correct, then space may not be fundamental. The three-dimensional arena in which we live, move, and perceive may be an emergent phenomenon, arising from a more fundamental description that operates on lower-dimensional surfaces. The depth we experience, the volume, the sense of insideness, all of this could be a projection, a hologram generated by information encoded on boundaries. This idea resonates with observations from quantum mechanics, where entanglement, the non-local correlation between particles, suggests that space is not as fundamental as we assume. Particles separated by vast distances can remain entangled, their states correlated in ways that seem to transcend spatial separation. Some researchers have proposed that space itself emerges from patterns of entanglement, that the geometry of spacetime is a consequence of how information is distributed and correlated across quantum degrees of freedom. In this view, the event horizon is not merely a boundary in space. It is a surface where the emergent nature of spacetime becomes explicit. The freezing of time at the horizon reflects the fact that the information about the infalling object is being redistributed, transitioning from a description in terms of three-dimensional trajectories to a description in terms of two-dimensional boundary data. The horizon is where the holographic nature of reality becomes undeniable. The cosmic storage capacity of the event horizon is staggering. A supermassive black hole, with an event horizon measured in billions of kilometers, can store an amount of information proportional to its surface area in Planck units. This is an inconceivably large number, far exceeding the information content of all the stars, planets, and galaxies that fell into it. The horizon is a near-perfect information storage device with a density of information at the Planck scale that represents the absolute limit allowed by physics. And as the black hole evaporates, this information is slowly released. The Hawking radiation carries correlations that, in principle, encode everything that ever fell in. The process is incredibly slow. For a solar mass black hole, the evaporation timescale is longer than the current age of the universe by many orders of magnitude. For supermassive black holes, it is even longer. But eventually, the black hole radiates away completely, leaving behind only the thermal glow of its final moments and the information encoded in the emitted radiation. This suggests a kind of conservation law for information at a cosmic scale. Nothing is truly lost. Everything that crosses the event horizon is recorded, encoded holographically on the surface, and eventually returned to the universe through Hawking radiation. The frozen image at the horizon is the visible manifestation of this recording process. A reminder that the boundary is not a point of destruction, but a point of transformation. The holographic principle also reframes the nature of the singularity at the center of the black hole. In classical general relativity, the singularity is a point of infinite curvature where the equations break down. But if the interior is holographically encoded on the horizon, then the singularity may not be a feature of the fundamental description. It may be an artifact of trying to describe the interior using classical geometry, a sign that the classical picture is incomplete. Quantum gravity, when it is fully understood, may reveal that the singularity is smoothed out by quantum effects, replaced by a region of extreme but finite curvature. Or it may show that the singularity is not inside the black hole in the usual sense, but is instead a feature of the boundary description, a mathematical object that represents the maximal encoding of information on the horizon. The true nature of the singularity remains one of the deepest mysteries in physics, intimately connected to the holographic nature of the event horizon. What is clear is that the event horizon is more than a passive boundary. It is an active participant in the structure of reality, a surface where information is encoded, preserved, and eventually released. The freezing of time at the horizon is not an illusion. It is the signature of a fundamental process, the transformation of three-dimensional information into a two-dimensional holographic record. This revelation shifts the entire narrative of the black hole. It is not a drain, not a destroyer, not a cosmic eraser. It is a recorder, a keeper of information, a boundary where the universe's data is compressed, encrypted, and stored with maximal efficiency. The frozen object at the edge is not suspended in time for eternity. It is being transcribed onto the horizon, its information preserved in a form that will persist as long as the black hole exists and will eventually be returned to the cosmos when the black hole fades. The holographic principle suggests that every event horizon in the universe is a library, a repository of everything that has ever crossed it. And if the principle extends to the entire universe, as some theories propose, then the cosmos itself may be a hologram, with all of reality encoded on a distant boundary, projected inward to create the rich, three-dimensional experience we inhabit. The frozen horizon is not the end of the story. It is the beginning of a deeper understanding, a recognition that the boundaries of spacetime are where the true nature of existence is written, encoded in the geometry of surfaces, waiting to be read. There are places in the universe where tomorrow never comes. This is not poetic exaggeration. It is a literal consequence of the geometry of spacetime. The event horizon of a black hole represents a boundary beyond which the concept of future, as understood by the outside universe, ceases to have meaning. An object falling across that threshold enters a region where its timeline diverges permanently from ours, where the ticking of its clock no longer synchronizes with any clock we could ever observe. For that object, time continues. For us, watching from outside, time stops. The object is frozen at the boundary, suspended in a moment that stretches toward infinity, never completing its crossing in our frame of reference. This creates a strange asymmetry in the fabric of reality. The universe contains regions, billions of them. scattered across galaxies where the past is forever preserved and the future is forever unreachable. Every particle, every photon, every fragment of matter that has ever approached an event horizon remains there. In a sense, encoded on the surface, visible in principle to distant observers as a fading, red-shifted ghost. The black hole becomes a repository of frozen moments, a library of events that have not yet concluded from the perspective of the outside world. But the objects themselves experience something different. They cross the horizon without hesitation, without noticing any boundary. They continue into the interior, moving inexorably toward the singularity at the center. Time for them flows normally. The future unfolds, cause leads to effect. The passage from one moment to the next proceeds as it always has. The clock does not stop. It simply continues along a trajectory that no longer intersects with the timelines of those who remain outside. These two narratives, the outside perspective, where time stops, and the inside perspective, where time continues, are both true. They are not contradictory, but complementary. Two views of the same geometric structure described from different vantage points. The event horizon is the surface where these perspectives diverge irreconcilably, where the unity of time fractures into incompatible timelines. Humanity has always sought to understand time. Ancient civilizations tracked the motion of stars and planets, constructing calendars to impose order on the passage of days and seasons. Philosophers debated whether time was real or illusory, whether the past and future existed or only the fleeting present. Scientists measured time with increasing precision, building clocks that could mark intervals down to billionths of a second, discovering in the process that time was not the absolute constant they had assumed. But the event horizon reveals something deeper. It shows that time is not merely relative or flexibly, is contextual. It depends not just on velocity or gravitational field strength, but on causal structure. There are regions of spacetime that are causally disconnected from others, separated not by distance, but by the impossibility of signal transmission. The event horizon is such a boundary. It divides the universe into regions that can communicate and regions that cannot. And this division is enforced by the geometry of time itself. For beings like us, confined to the outside of the horizon, this means there are questions that can never be answered. What happens inside a black hole? What does the singularity look like? How does time behave in a region where space-time curvature becomes infinite? These are not merely questions awaiting better instruments or more advanced theories. They are questions that the structure of the universe renders unanswerable from our perspective. The information is there, encoded in the interior geometry, but it is causally isolated from us. No signal can return. No message can escape. The answers exist in a region of spacetime that is, for all practical purposes, beyond the edge of the knowable universe. This limitation is humbling. We are accustomed to thinking of the universe as something that can be explored, mapped, understood. We send probes to distant planets, telescopes peer billions of light years into the past. And we construct theories that describe the behavior of matter at scales ranging from the subatomic to the cosmological. But the event horizon is a reminder that there are boundaries to exploration, not imposed by technology or time, but by the fundamental structure of reality itself. And yet, this boundary is not a wall that isolates us from understanding. It is a window into the nature of spacetime. By studying the behavior of matter and light near the horizon, by measuring the redshift and time dilation, by observing the accretion disks and jets, we learn about the geometry of the universe in its most extreme state. The event horizon teaches us that time is woven into space, that the two cannot be separated, that what we perceive as the flow of time is a feature of the path we trace through spacetime. The existence of black holes also forces a reckoning with the concept of eternity. In everyday language, eternity suggests an infinite duration time that goes on forever. But the event horizon presents a different kind of eternity, a moment that never concludes. The object falling toward the horizon is, from our perspective, eternally in transit. perpetually approaching but never arriving. Its final crossing recedes infinitely into the future. This is not immortality in the sense of endless life, but a kind of temporal suspension, a freezing of narrative progression. For the object itself, eternity has a different character. Once inside the horizon, its future is finite. It will reach the singularity in a measurable amount of proper time seconds, minutes, or hours, depending on the mass of the black hole. But this finite future is unreachable from the outside. The object's timeline has branched away from ours, entering a region where the geometry ensures that every future moment leads deeper inward until time itself ends at the singularity. This duality, finite for the infalling observer, infinite for the distant observer, captures the essential strangeness of the event horizon. It is a place where the word when loses its universal meaning. When does the object cross the horizon? The answer depends on who is asking. For the object, it crosses at a specific moment in its own timeline. For the outside observer, it never crosses, remaining forever at the threshold. Both answers are correct, and neither can claim priority. This fragmentation of time challenges the human desire for a unified narrative. We want the universe to tell a single story, to have a definite sequence of events that all observers can agree upon. We want to know what happened, when it happened, and in what order. But the event horizon denies us this comfort. It insists that there is no single story, no universal timeline, no objective sequence that spans both inside and outside. There are only perspectives, each valid within its own frame, each describing a different slice through the four-dimensional structure of spacetime. This realization has philosophical weight, suggests that reality is not the objective, observer-independent structure we often imagine. Instead, reality is relational. It depends on where you are, how you are moving, and which part of spacetime you can access. The universe does not present itself the same way to all observers. What is present for one is past for another. What is simultaneous for one is sequential for another. What is future for one is unreachable for another. The event horizon is the most extreme example of this relativity, but it is not the only one. Every observer, by virtue of their position and motion, occupies a unique perspective on spacetime. The present moment you experience right now is not shared by someone on the other side of the galaxy. Their present is tilted relative to yours, encompassing events you consider past or future. The universe is not a shared stage, but a collection of overlapping perspectives, each carving out its own present from the four-dimensional whole. Living in such a universe requires a shift in how we think about existence. We are accustomed to thinking of objects as persisting through time, as having a continuous identity that links their past, present, and future. But near a black hole, this persistence becomes ambiguous. The infalling object persists from its own perspective, continuing its journey inward. But from the outside perspective, it is frozen, never completing its transition. Suspended in a state that neither fully exists in the present nor fully recedes into the past. This ambiguity extends to the question of whether the black hole itself has changed. From the outside, when matter falls in, the black hole's mass increases, its event horizon expands, and its gravitational influence strengthens. These changes occur on observable timescales, measurable by distant observers. Yet the matter that caused these changes appears from the same perspective, never to have crossed the horizon. How can the black hole have absorbed something that has not yet entered it? The answer lies in the holographic encoding. The information is transferred to the horizon as the object approaches, and this transfer is sufficient to alter the black hole's properties. The object need not be inside in a classical sense for its effects to be felt. This holographic transfer blurs the boundary between inside and outside in subtle ways. The black hole is defined by its event horizon, a surface that marks the point of no return. But the horizon is not a fixed structure. 'Tis a dynamic surface, growing whenever energy or matter falls in. It's potentially shrinking if the black hole emits Hawking radiation faster than it accretes. The horizon is less like a solid boundary and more like a moving frontier, constantly adjusting its position in response to what approaches it. And this frontier is also a temporal threshold. To cross the horizon is to step from one causal regime into another, from a region where escape is possible to a region where it is not. The transition is smooth from the infalling perspective, but from the outside perspective, 'tis asymptotic, stretched across infinite time. The horizon is where the geometry of spacetime bends so severely that these two perspectives can no longer be reconciled into a single coherent narrative. Humanity's position in the universe is one of safety. We orbit a stable star, far from any black hole, insulated from the extreme curvatures that distort time. Our clocks tick at a rate that seems absolute to us because the deviations from flatness are so small. We experience time as linear, predictable, universal. This is the gift of living in a gentle gravitational field. But it is also a limitation. It obscures the deeper truth that time is not a fixed river, but a flexible dimension shaped by mass and motion, capable of slowing, bending, and even stopping under the right conditions. The event horizon exists as a reminder of this deeper truth. It stands at the edge of the universe's structure, a boundary where the familiar rules break down and the hidden nature of spacetime becomes explicit. It is a place we will likely never visit, a threshold we will probably never cross. But its existence shapes our understanding of the cosmos. It tells us that the universe is stranger, more subtle, more geometrically rich than everyday experience suggests. And it tells us that time, which feels so immediate and personal, is not ours alone. It is a dimension we share with the rest of spacetime, a coordinate woven into the fabric of reality, subject to the same curvatures and distortions that affect space. The passage of time is not an absolute progression, but a path through geometry, and that path can be bent, stretched, and severed by the presence of mass. The black hole is a monument to this principle. It is a region where mass has been concentrated so intensely that spacetime cannot resist. The curvature becomes so extreme that time itself is pulled inward, dragged toward a singularity where the familiar coordinates cease to function. For those outside, the black hole appears as a frozen surface, a boundary where time slows to a halt and objects linger eternally on the edge. For those inside, it is a passageway to a region where the future is a fixed destination and escape is geometrically impossible. Both perspectives are real. Both are valid descriptions of the same physical structure, and neither can claim to be the complete picture. The black hole is a phenomenon that transcends any single viewpoint, a manifestation of space-time geometry that can only be understood by embracing the multiplicity of perspectives that relativity demands. In the end, the event horizon is a place where the sequence of moments, the familiar flow from past to future, reaches its limit. It is the boundary where the clock stops, not because it breaks, but because the geometry of time itself has been bent into a shape that no longer permits forward progression in the outward direction. It is a place of stillness in the eyes of the distant universe, and a place of inevitable motion for those who cross it. It is the end of the sequence for us, and the beginning of a different sequence for those who venture beyond. We may never know what lies inside. We may never witness the crossing from the perspective of the infalling traveler. But the horizon teaches us enough. It teaches us that time is not what it seems, that the universe contains pockets of profound strangeness, that the boundaries of space-time are also the boundaries of knowledge. It teaches us humility that our experience, however vivid, is a narrow slice of a much larger reality. And it teaches us wonder, that in a cosmos governed by elegant equations where geometry and gravity intertwine, there exist places where clocks freeze, where light cannot escape, where the future becomes unreachable and the past is preserved in an eternal fading glow. These places are not anomalies. They are features of the universe, woven into its structure, predicted by the same laws that govern the stars and planets. They are the event horizons, the thresholds where time stops, where the journey inward becomes a journey without return, and where the cosmos holds its deepest secrets in a silence that will never break.